Yeah, and we can even see that visually here. So here we see some pairwise distances of a sample of 105 instances, sorry, drawn from a uniform distribution between 0 and 1. And you see here the dimensionality grows from 1 dimensions to 10 to 100 to 1000. So this is a logarithmic scale, obviously, here. And the whole thing is normalized here to 1 times square root of d, which is the factor that we expect the distances to grow, so that everything is somehow comparable. And we see here different things. So here we see the mean plus the plus minus the standard deviation. So the red one here is the mean value, which basically remains the same as we since we normalized it here. So we expect it to grow by a factor of square root of d. If we normalize it by 1 times square root of dimensionality, we expect it to be quite constant, which is the case. Yeah. So actually the mean value scales exactly as, or grows exactly as we expected. Yeah. And you see here plus minus the standard deviation is the dashed are the dashed limits. So the standard deviation or the variance actually diminishes, exactly what we expected here. That's exactly what the precondition actually states. Yeah. And in that case, we see that the distance to the maximum, to the farthest neighbor, which is the green dashed line here, and the distances to the nearest neighbor, which is the blue dashed line here, are actually also becoming more or less the same. And that's exactly the point that now we get here. We get these two distances within a limit of 1 plus epsilon. Yeah? We get these two distances in between these two circles here. That's the point. Yeah? And we see that even here experimentally with some synthetic data if we just measure it. Yeah? Those are the average nearest neighbor distances and the average farthest neighbor distances of 105 points in different dimensionalities. Yeah? So that's exactly the point, or the point that is stressed here. Okay, so once again, be clear about the preconditions of the theory, of the theorem of this concept here. So we consider the feature space of to be of d relevant features for a given application. Yeah, so the truly similar objects display small distances in most of the features, then the features are really relevant. So now if we add d times c additional features which are completely independent of the initial feature space, meaning their relevancy is absolutely zero. Yeah, the relevancy to our pattern is absolutely zero, meaning that we just add random noise more or less. Yeah, then with increasing c, the distance in the independent subspace will dominate the distance in the complete feature space. Yeah, so if we, for example, have 5 super relevant features, everything is fine. If we have 500 super relevant features, everything is fine. No cursive dimensionality, no concentration problem and stuff like that. Neighborhoods are still absolutely okay, yeah? Because all of those features are relevant to our pattern, meaning they have small distances for similar objects and high distances for not so similar objects. So if we now add to those, say 5 or 500 or whatever, say 50, to these 50 super relevant features, if we now add 50, 100, 150, 500, whatever, how many ever, totally irrelevant features, meaning totally random features, yeah, for each object, then if we increase this addition of irrelevant features, we run into those problems, because at some point we have too many irrelevant features that somehow dominate the relevant features, yeah, the relevant ones. Yeah? So then of course the irrelevant features do exactly these cursing things. Yeah, so they actually enable or leverage these problems here with unstable neighborhoods, distance concentrations and stuff like that. Yeah. So the question, of course, is how many relevant features must be similar to indicate object similarity, or how many relevant features must be dissimilar to indicate dissimilarity, yeah, or distance. That is, of course, a good question, sometimes not so easy to answer. But anyway, with increasing dimensionality, of course, the likelihood that two objects are similar in every respect, of course, gets smaller, meaning that if we add new features, it's likely that we add something which is not relevant, which is irrelevant, especially if we just add it because we have it and not thinking about the relevancy of features. Yeah? So the whole text I just told you is everything about the relevancy of features. Yeah? If we have a lot of relevant features, everything's fine, no curse of dimensionality, at least no problem with unstable neighborhoods and distance diminishing and stuff like that. But if we add irrelevant features, we have exactly those problems like unstable neighborhoods, distance concentration problems and stuff like that. Yeah? So we have to keep that in mind. Yeah, next problem is growing data space. Okay, we know, of course, the data space grows with increasing dimensionality. What are exactly the problems? Well, first of all, in low-dimensional spaces, we have at least some intuitive assumptions on the behavior of volumes like spheres or cubes and stuff like that, and especially about the distribution of points within a sphere or within a cube or stuff like that. Yeah? I mean, the data space, if it's a data space normalized between 0 and 1, it's also a kind of cube. Yeah? And for lower dimensional spaces, we have some kind of intuitive ideas what actually happens with special distributions within a cube or a sphere or whatever. Yeah? But we'll see that these basic assumptions do not hold in high dimensional spaces. So spaces become extremely sparse, or even a lot of spaces or parts of the space, of the data space, are absolutely empty. There's nothing in it, no points. Yeah? And the probability of one object inside a fixed range, of course, also tends to be 0. Yeah? So if we have a high dimensional data cube and say 100 points in it, and we slice out a small subcube, the probability that there is nothing in is extremely high. And of course, if we add dimensionality, if we add dimensions, the cube grows. We still have only 100 points to distribute in the cube, and the cube grows with growing dimensionality. Of course, the probability that something is in a small fixed subcube becomes 0 very, very soon. Yeah? We'll talk about that right in a minute. And also the distribution of data has a strange behavior. Yeah? For example, a normal distribution has only few objects in its center, and the tails of the distributions become more and more important. Wait a minute. A normal distribution, yeah, that's a Gaussian distribution. A Gaussian distribution, we know this characteristic curve, yeah, so the highest probability to observe objects from a Gaussian drawn from a Gaussian distribution are around the mean, which is typically the center of at least the center of the distribution. Now, in high dimensional cases, so we don't have these characteristic curves anymore, where the tails have the low probabilities, and the center around the mean have is high probability range. It's the other way around. At the tails we have high probability, and around the center we have low probability, or at least lower probability. Completely unintuitive, but actually that's exactly what happens. And we have a closer look on these issues in order to somehow get at least an intuition for that, which is counterintuitive because it's against our original intuition.